In the remote reaches of the earth, where winds howl relentlessly, begins the tale of humanity's struggle to harness the wild forces of nature. Here, there is no room for weakness, for the winds that will generate energy are the same fierce enemy that seeks to demolish any structure standing in its path. And before laying the cornerstone, engineers embark on studying the invisible symphony of air for many long years, measuring wind speeds with extreme precision, monitoring its violent fluctuations. Each meter per second translates into millions of watts of potential energy. And then everyone realizes that the ground here is not merely dirt, but the foundation that will support hundreds of tons. So geologists survey the deep layers of Earth, searching for solid rock capable of absorbing the enormous vibrations caused by the continuous rotation of the turbine. The project is ambitious to the point of fantasy. We're talking about a structure that reaches toward the heavens, rising higher than skyscrapers, weighing as much as fleets of commercial aircraft. It's a battle calculated in numbers against gravity and torque. As work progresses, the first logistical challenge emerges: accessing the site itself. Special roads are carved through rough terrain, engineered with precision to bear giant trucks carrying loads of exceptional length and weight without tipping on the turns. Then begins the battle with the earth through excavation, with fleets of excavators working in harmony to remove thousands of cubic meters of soil and rock, clearing the space necessary to plant the roots of this mechanical giant deep into the earth. During this time, every centimeter of excavation is calculated with precision. A mistake here means an engineering disaster later. The pit must be wide and deep enough to accommodate a massive concrete block that serves as an anchor, preventing the turbine from toppling in the fiercest storms. Afterward, the soil at the bottom of the pit is compacted violently to ensure it's level and solid. This compressed layer is the last line of defense against subsidence that could cause the tower to tilt even slightly, meaning failure of the entire project. Then, a thin initial layer of concrete is poured, a leveling layer that sets the stage for the major operations, ensuring complete isolation between the reinforcing steel and ground moisture, protecting the metal from rust that could corrode the structure's bones. After these preparations, steel shipments arrive, tons of reinforcement bars that will form the skeletal structure of the foundation. Iron and concrete will unite to form a composite material resistant to tensile and compressive forces that neither could face alone. At the heart of the foundation, the anchor cage is assembled, a circular ring of giant steel bolts. This is the most vital part, the critical connection point that will bind the towering steel structure to the buried concrete base. To ensure perfection, the anchor cage's levelness is adjusted using advanced laser equipment. The tolerance for error here is nearly non-existent. A 1 mm tilt in the foundation will translate to a deviation of meters at the turbine's tip, threatening its dynamic balance. Workers then begin, like skilled weavers, weaving a complex network of reinforcement steel around the cage, with bars interlacing and crossing at calculated angles to distribute loads coming from above and disperse them evenly throughout the earth below. From above, the design resembles a giant eye. This radial distribution of steel isn't random. It's a direct application of physics laws to reduce stress concentration at any point, preventing concrete from cracking under pressure. As night falls, steel bars gleam under floodlights, announcing the completion of the skeletal structure and its readiness for the decisive next phase. In the calm before the storm, as everyone prepares for the continuous concrete pour that allows no stops. With dawn's arrival, a fleet of cement mixers lines up in an operation resembling a massive blood transfusion. Once pouring begins, it cannot stop until the foundation is complete, to avoid creating pour joints that could be fatal weak points. At those moments, concrete pumps roar, their long arms like artificial arteries stretching over the steel network, and the thick gray liquid begins flowing, a precise chemical mixture of cement, gravel, and additives, ensuring maximum hardness. As concrete flows, filling every gap, embracing the steel firmly, it becomes clear that this union is the secret to reinforced concrete's strength. Steel handles tensile forces from the tower's swaying, while concrete bears enormous compressive forces. Meanwhile, workers dive into the wet mixture with mechanical vibrators, aiming to expel trapped air bubbles that could form hollow pockets. Every void is a potential weak point that could cause foundation cracks after years. The operation continues for hours, as hundreds of tons of concrete pour without interruption in a race against time and chemical reactions. New layers must bond with old ones before they begin drying. As the concrete hardens, engineers monitor heat released from the chemical reaction. If temperature rises too quickly, the foundation could crack internally, so cooling is controlled with surgical precision. As the massive mass hardens, craftspeople manually level the upper surface, which must be smooth and perfectly flat to receive the first piece of the steel tower with no room for deviation. Then the foundation is covered with insulating blankets to maintain ideal moisture and temperature. This critical period, known as curing, allows chemical bonds within the concrete to grow and reach maximum hardness and durability. Over days, the concrete's color gradually shifts. What was liquid has now become an artificial stone, weighing thousands of tons, ready to withstand nature's forces for decades without budging. In laboratories, samples from the same mixture are crushed to confirm they've met required standards. Work cannot proceed to the next phase until numbers prove the foundation can handle incredible pressures. Then the pit is backfilled around the concrete foundation, hiding this colossal engineering work underground again, with only the central bolt ring visible. Yet the turbine's stability depends entirely on this buried giant. After that, soil around the backfilled foundation is compacted to ensure it bonds with surrounding earth. Now the foundation has become an integral part of the site's geology, where human engineering has unified with natural rock. A new phase begins with the arrival of the main crane components. This crane itself is an engineering marvel, the only one capable of lifting heavy weights to towering heights amid relentless winds. The crane's giant arm is assembled on the ground piece by piece. Assembling the crane requires a smaller auxiliary crane, depicting the hierarchy of mechanical strength needed to construct a structure this size. When the crane stands upright, casting long shadows across the site, it becomes the tallest structure in the area, ready for precise lifting maneuvers that defy physics and challenge violent winds. Trucks then arrive carrying tower sections. The lower section alone weighs dozens of tons, made from hardened steel and coated with special protective layers to resist corrosion and rust for 20 years. Meanwhile, engineers inspect the flanges metal rings at the section ends, which must be perfectly flat and flawless, as these surfaces will be connection points transmitting loads through the tower. The lower section is then bound with massive steel chains, each link tested to handle weights exceeding the section's own weight. Safety here is paramount with no room for risk. When the crane's engine roars and steel cables begin tensioning, the massive steel section slowly leaves the truck's surface, suspended between earth and sky, at the mercy of the operator's skill and calm winds. A ground crew directs the suspended section using guide ropes, attempting to control its swaying, aiming to lower it precisely to match the bolt ring protruding from the concrete foundation. The moment of truth comes when the holes in the tower's base align with the ground bolts, where metal slides against metal in a tight engineering embrace, beginning the fastening process that will permanently attach the tower to the earth. Workers use giant hydraulic torque wrenches to tighten the nuts, not randomly, but with precisely defined force measured in Newton meters, ensuring each bolt carries its fair share of stress. After tightening each nut, a paint mark is applied. This simple procedure is a quality signature, visible proof to inspectors that this point has been secured and passed final inspection. Inside the tower's base, installation of the electronic brain begins. Control panels, transformers, and massive cables that will later transmit energy, generated above, to the electrical grid below. Internal stairs and service elevator tracks are also installed. This tower isn't merely an empty tube, but an integrated vertical building that technicians must regularly climb to perform routine maintenance. Then the second section rises, and with each additional section, challenges increase. Wind speeds grow with altitude, making control of the suspended piece more difficult, requiring real-time coordination between the crane operator and guides. As workers stand on the edge of the first section, suspended in air, awaiting the second section's descent, their courage seems as important as machine precision. They'll perform the final alignment between the giants. Then, the two sections are connected with internal high-strength bolts. This connection must resist shear and bending forces the tower will experience when winds strike the blades with hurricane force. Vibration dampers are added inside the tower. These suspended masses act like reverse pendulums, absorbing frequencies that could cause tower resonance and collapse, achieving required dynamic balance. The tower's work is halfway complete, the structure growing ever more imposing, beginning to command the horizon. But the hardest part hasn't come yet. Upper sections are lighter but more vulnerable to wind manipulation. During the third section's lift, winds caress the load, causing dangerous swaying. The crane stops momentarily as everyone holds their breath, waiting for the storm to calm. Patience here is the key to survival. With each new section, suspended electrical cables within it are connected, thick cables forming the backbone for energy transmission, requiring careful insulation and fastening to prevent friction against the tower's walls. Then the final upper section is prepared, featuring a conical design to receive the generation chamber, where manufacturing precision reaches fractions of a millimeter to ensure complete compatibility with mechanical components. The final ascent of the tower's body begins. The crane, now working at maximum extension, winds above, playing a forceful melody, a delicate mechanical dance at heights exceeding 300 feet. From the summit, trucks appear like tiny ants as the final section is secured, completing the turbine's backbone. The stage has been built, and it's time for the main performer to arrive, the nacelle. And here arrives the nacelle, or the housing, the very heart and mind of the turbine. This chamber is about the size of a small house, containing the generator, the gearbox, the braking systems, and its weight alone exceeds 100 tons. The moment it arrives, protective covers are removed, revealing a delicate and intricate engineering marvel. Each component here is designed to operate under harsh conditions, from the extreme heat of friction to the freezing cold of stormy weather. Sensors and wind measurement devices are then installed atop the nacelle. These are the turbine's eyes that will read the atmosphere and give orders to direct the blades toward the wind to extract the maximum possible energy. At the base of the nacelle sits the yaw system's gears. These massive gears allow the entire head to rotate 360 degrees to track wind direction, and they're made from special alloys that withstand the stress of constant rotation. Then, preparations begin for the heaviest and most dangerous lifting operation. Securing the nacelle requires precise balance calculations of its center of gravity. Any miscalculation could cause it to strike the tower during ascent. The enormous mass rises very slowly as crane cables groan under pressure, and motors operate at maximum capacity, a scene that embodies the pinnacle of industrial force confronting gravity. Midway through, the nacelle appears to be floating in space, and the apparent stillness masks intense tension among the crew. A single mistake now would cost millions and set the project back by months. At the peak, an elite team waits. These technicians working at dizzying heights, ready to receive the heavy load and guide it to rest precisely on its bearing ring. Then, remarkably gently, the nacelle touches the tower's top, carefully positioned so its gears settle into place. The mechanical system engages with the fixed structure, the head joining the body. From inside, technicians rush to secure the yaw system's bolts. This connection is the vital joint, allowing the turbine to move, and it must be strong enough to resist enormous torsional forces. Next, the main power cables from the generator are connected to those running down the tower, with cables suspended in a special loop that allows them to wind freely without breaking when the turbine rotates around its axis. Then arrives the hub, the cone-shaped nose, where the blades will be mounted. This massive spherical component is the motion conversion point, where linear wind movement transforms into rotational torque. The pitch bearings are carefully inspected. These bearings allow each blade to rotate around its own axis, changing its attack angle with the wind, a critical technique for controlling speed and braking. The hub is so large that workers enter inside it to make connections, and from within, it resembles a small submarine filled with hydraulic and electrical systems that will control the blade's movement. The hub is lifted for installation at the front of the nacelle, where the main rotating shaft must align with micrometer precision. Any deviation will cause vibrations that destroy the gearbox in record time. The hub is secured to the main shaft with massive bolts tightened with enormous hydraulic force, because this connection will transmit all the wind's energy into the generator. Inside the nacelle sits the electrical generator. Whether powered by permanent magnets or copper windings, this component performs the physical magic, converting mechanical motion into a stream of electrons. The gearbox serves as the powerful intermediary, since wind rotates slowly and the generator needs high speed. The gears multiply rotation speed 100-fold, while enduring pressures and friction generating heat sufficient to boil water. To overcome the heat, the nacelle is equipped with advanced cooling systems and external radiators, ensuring oils and electronic components maintain safe operating temperatures. Now comes the most impressive and complex transport component, the blades, each exceeding 50 or 60 meters in length, requiring specialized trucks and complex maneuvers to navigate mountain passes. The blades aren't merely plastic pieces, but engineering masterpieces of fiberglass, carbon fiber, and composite materials, incredibly lightweight for their size, yet strong enough to resist bending. The blade design draws inspiration from aircraft wings, with aerodynamically calculated curves allowing them to lift and rotate even with the gentlest breezes, maximizing turbine efficiency. Since they'll be the highest points in the area, lightning conductors are installed at blade tips. These conductors absorb the enormous electrical charges from storms and safely conduct them down the tower to Earth. Then, the special lifting apparatus is secured around the blade's middle, cradling it gently yet firmly, distributing pressure to prevent the thin composite structure from shattering during lift. The first blade begins rising, bending slightly under its own weight. This is natural and intended, as flexibility is the secret to survival against variable wind impacts. Above, the hub rotates into a perfectly horizontal mounting position. This coordination between ground and peak is necessary for smoothly inserting the blade bolts into the hub's holes. The giant blade approaches the hub in what appears like threading a needle, except on a massive industrial scale at hundreds of feet above ground. Workers inside the hub receive the protruding bolts from the blade's base, guide them into position, then begin fastening the massive nuts that will hold the blade for decades. Dozens of bolts surround each blade's base, all tightened in a specific sequence, ensuring even pressure distribution on the circular bearing, allowing the blade to rotate smoothly around its axis. Then, the crane releases the first blade, and the turbine now has a single arm extended skyward. This imbalance creates enormous stress on the braking system, so the remaining blades must be installed quickly. The hub then rotates exactly 120 degrees. This rotation requires enormous hydraulic force to overcome the first blade's weight, now in a tilted position. The second blade rises as increasing wind speeds make the operation more dangerous. The blade acts like a giant sail, capturing wind, threatening loss of control from the crane. The ground crew pulls guide ropes with all their strength to resist wind pressure, a battle of muscles and physics, keeping the blade parallel and steady to the hub above. The second blade installs successfully, and the turbine takes a giant V shape. Yet balance remains missing. The structure awaits the third blade to complete geometric symmetry. Another hub rotation follows. The weight is now massive and unbalanced, with the gearbox bearing enormous torque to position the third blade's mounting point for proper horizontal installation. As sunset approaches, the final blade rises, the finishing piece of the artistic composition, and with its installation, the circle closes and the giant rotor completes. The last blade slides into place, and for the first time, the magnificent three-pointed star shape stands complete in the sky, transforming the project from scattered parts into an integrated machine. Then, the giant crane withdraws, folding its long arm. Its work is done, leaving behind a monument touching the clouds. The age of mechanical muscles ends, and the age of electronic minds begins. Inside the nacelle, work continues relentlessly, as electricians connect thousands of wires to complex control panels. These wires are the nerves transmitting sensor signals and operating commands. At the tower's base, the massive electrical transformer is installed, its function raising the generated electrical voltage to match the national transmission grid and reducing losses during the long journey across cables. The turbine connects to a network of buried cables, this hidden system linking the entire wind farm, collecting the output of dozens of turbines into a single stream of clean power. Software engineers connect their computers to the central SCADA system. This system is the mastermind, monitoring everything from oil temperature to wind speed, enabling remote control from great distances. Then, operational testing begins. The first test is positioning, with the nacelle rotating slowly and quietly to face the wind, responding precisely to commands like a tamed beast. Next comes blade angle testing, watching the blades rotate around themselves, adjusting angles to slice the air sharply or to block its path. This graceful movement is the secret to controlling extracted energy. The critical moment arrives with brake release, as wind begins pushing the blades and the rotor disc turns slowly and heavily, the turbine's first breaths, the first rotation in a lifespan stretching 20 years. Inside, the gears come alive, and the blade's slow movement transforms into frenzied rotation inside the generator as mechanical energy flows through the system. On control screens, the power output indicator jumps, the numbers climbing from zero, scaling the graph. The conversion succeeds, and electrons begin flowing toward the grid. Outside, the turbine rotates at full operating speed, blade tips cutting air at speeds exceeding 200 kilometers per hour, emitting a distinctive sound testifying to its power. At night, red warning lights flash atop the nacelle to alert aircraft, and the turbine stands like a giant guardian in darkness, continuously generating power in silence and steadiness. Seasons will pass, storms will rage, snow will fall. Yet this engineering monument will endure, designed to withstand and transform nature's fury into energy-illuminating cities and powering factories. From mere concept and blueprints to a hole in the ground, then a structure embracing the sky, every bolt, every ton of concrete, every electronic chip contributed to building this miracle. This turbine isn't alone, but part of a fleet harvesting the wind, together representing a giant step toward a clean future and a triumph of human intellect that harnessed Earth's forces without destroying them.